Hey, welcome back, everyone. Ready for your last organic chemistry lecture? Heaven knows I am. Well, again, I might make another optional one from chapter 29 for you guys, maybe next week sometime. But more importantly, just a reminder, the material in this video will not be on our exam number 4. This is all fair game for the final exam. I'm just trying to get it done early so that I can focus on writing exams and administering exams and grading exams and all that other stuff. So I can focus more on those things. So I know I am aware of how often I say during the term, for those of you going on to biochemistry, and I know there's a significant number of you. It's a minority, but it's a significant minority. It's not one or two of you that have no intention ever of taking biochemistry and are not interested in that side of life, probably going into something involving material science or engineering. You've been very patient and you've put up with all that, and so this lecture is for you. This one is about polymers. Polymers, of course, being only one of the most important technological advances of the previous century, the 20th century. You just look around you in the room you're in and consider how many things are made of man-made molecules. Well, I would not be surprised if you found that the answer was most of them. I'm scrolling through here some of these definitions. I just left them in the class notes so that you can be aware of them. Again, I would say, especially for those of you going on in engineering or material science, those are going to be some important ideas. We're going to cover how it is that two main types of polymers are made. One type is called chain growth or addition polymers. And those, the macromolecule that you eventually get contains all of the atoms from the original monomer units. And then you've also got step growth polymers, which are also called condensation polymers. And those are going to form long polymer chains that do not contain all of the atoms in the original molecules. Generally, there's some kind of a small molecule that winds up being given off at the end. Often that's water or HCl or something like that. And so you lose a whole bunch of these small molecules and you get a long polymer chain as the result, maybe thousands or tens of thousands or hundreds of thousands of residues long. So usually addition polymers are made by radical reactions. So if you've forgotten about those and how we write their mechanisms, please review them from the previous term. Well, and not only in chapter 8, where we didn't really cover it as much, but I know that we covered radical reactions in some earlier chapter, try 6, but I know that we covered them in Organic 1. So usually these are initiated by heat or some kind of radical initiator like an organic peroxide or hydroperoxide. And an example of a very famous addition polymer is polyethylene, would certainly be one of them, where the monomer is just ethylene, CH2 double bond CH2. One derivative of polyethylene is polystyrene. So we start with, if you will, N molecules of styrene, and we undergo radical polymerization, and we get a product that looks like this. Now, please notice you need to know how to draw structures of polymers. And the rule that you need to know for drawing polymer structures is that you'll draw parentheses. That's one thing. You need parentheses. You also need to write an N after the parentheses. And that N just signifies that whatever is going on inside the parentheses happens N times repeatedly. You get one of these, then another one, then another one, then another one, then another one, arbitrarily many times, corresponding to however many molecules went into that chain. And the third thing that you need to know, the third rule about drawing these, is inside the parentheses, you need to put every single atom that occurs in the repeating unit of the polymer exactly once. You need to put every single atom that occurs in the repeating unit exactly once. And so the way you make an addition polymers, generally these are going to be ethylene derivatives. What you wind up doing is turning the double bond into a single bond, And then those electrons in that bond are used to help form bonds on either side to another monomer unit. You'll see that when we go through the mechanism in just a moment. You'll see that what we get has basically a structure that looks like this. Now, I chose to put the phenyl group up here. It would be perfectly fine to put it in any of the other three locations. You see what I mean? That means exactly the same thing. That's yet another case of not only would I not take off points, but I wouldn't even notice. I would just see it as being the same thing and move on, which means you need to practice drawing until you see that those are the same thing and not different things. So it's important to be able to draw polymer structures correctly. Good, so what does the radical mechanism look like? Well, you may recall, and certainly will once you've reviewed, that radical reactions have three phases: initiation, propagation, and termination. And here I've put what you need to know about them. In the initiation step, well, this is initiated by a radical initiator, like an organic peroxide. You break that weak oxygen-oxygen bond either by heat or by light of an appropriate wavelength, and you get these alkoxy radicals. We'll go over the propagation step in a minute, and the termination step is just like any other termination step. Two of these radical chains will come together, join together the two unpaired electrons to make a bond and make an even electron species. There you go. There's a good reference, by the way. Looks like we covered that in chapter 6, as I thought. So what does the propagation step look like? Well, here's our alkene, in this case styrene, but it could be any ethylene derivative. And the alkoxy radical is going to add to the alkene and make another radical. And what that means is that you are going to have these, oh, I don't know, do you want to call them caps or end pieces that go on the ends of the polymer chain? And you can see that with these bonds that stick through the parentheses, right? This can't go on literally forever. There has to be something on the end. And they'll probably be whatever the alkoxy radicals are that come from the organic peroxide. But I think you'll agree if N is 50,000, then these alkoxy groups really don't matter. And so that's why we don't show them here. They're irrelevant. They're negligible in comparison to the structure of the whole of the polymer chain. Anyway, from this step, you get another radical. That now finds another molecule of your monomer and does the exact same thing as the peroxy radical did, and you get another radical, which finds another molecule of the monomer, and you get another radical, etc., etc., etc. And if you analyze this structure, I think you'll see that basically you're getting the same thing as over here, right? You get CH2s and PHCHs. So you get essentially the same structure as shown up there, but this is typically how we draw the structure of addition polymers. There are variations on this radical reaction that are cationic and anionic rather than radical. In the case of a cationic polymerization, you would need to treat your styrene or whatever your other or whatever your monomer is with a strong acid. Could be either a Bronsted-Lowry acid or a Lewis acid. This alkene will attack either the H plus or the Lewis acid, just like we learned that alkenes always do in chapter 8. And you'll wind up with a carbocation, which is a good Lewis acid. That carbocation will find another monomer molecule, and the double bond will come out and attack that carbocation, form a bond to make another carbocation. And that will find another monomer molecule, attack again, and so on and so on. You get the same thing, by the way. The structure of the product's the same. We call cationic polymerizations self-terminating because you don't need to do anything special. They will self-terminate just like the radical reaction will self-terminate when it runs out of starting material. In this case, all you need to go from that last cation, wherever it may be, to a neutral product, you just need something to act as a base in order to pull a proton off next to the carbocation. It looks like the last step of an E1 reaction, so you might want to review E1 reactions in chapter 11, and you get your neutral product. So that's how that works in a cationic sense. The anionic polymerization is the exact opposite. In this case, you would take a very strong nucleophile, maybe even like an alkyl lithium or a Grignard reagent, a carbanion, some stupidly strong nucleophile. Well, instead of the monomer acting as a nucleophile, now it's going to act as an electrophile. Your nucleophile will add into one of the alkene carbons, break the pi bond, and put the electrons on the next carbon, and you get a carbanion, which is a great nucleophile. So that attacks another monomer molecule, which forms another bond, breaks the pi bond, and makes a carbanion, which attacks another, and so on and so on. You see how this goes. Once again, you get the exact same compound. Whether it's radical, cationic, or anionic, you always get the same compound from it, no exceptions. It doesn't matter which mechanism you use, the product's the same. The only thing is we say that anionic polymerizations are living polymers, which sounds a little creepy. Of course, they aren't literally living. What that means is the process isn't self-terminating. Eventually, you need to quench the reaction by adding some weak acid, generally water, but some proton source like that will be added. And that will quench all of the carbanions, and then you can isolate your polymer. So much for addition polymers. One other issue that I think, again, will be of particular interest to engineers and material science majors is all of the different, well, first of all, you have the possibility of chiral carbons in the polymer chain. And not all of those chiral carbons need be created equal, right? The configuration at each of those carbons could, in principle, be either R or S configuration. And so there are essentially three possibilities for all of these. And this could even be a section of polystyrene that we made just above by a radical or cationic or anionic method. Either the monomers come in at random, and so there's no particular pattern to the stereochemistry, or there are also, and that is of course what we will get without any outside interference, such as adding the proper catalysts. And there are catalysts that will ensure that the addition always happens exactly the same, and so the resulting polymer has the exact same stereochemistry at every chiral carbon. There are catalysts that will do this for us, and as you can imagine, they are very, very spendy. There are also equally spendy catalysts that will make it exactly alternate, so that the stereochemistry alternates every time, each time another monomer molecule adds. And those three types of polymers are called atactic, isotactic, and syndiotactic, respectively. And this is going to be important, especially, again, for those of you involved at all in materials to know. As you can imagine, the structure of these three polymers will significantly affect the properties of the resulting polymer. And if I asked you guys which of these would be likeliest to be amorphous and which would be likeliest to be crystalline, I think you would all take a wild guess that the atactic polymer will be amorphous, no particular crystalline structure, and the isotactic and syndiotactic flavors are much likelier to be crystalline. And of course, that wild guess would be exactly right. So it's important in terms of structure and therefore properties of the polymers. Good, so I think that's all we need to say about that. I want to end with well, I don't want to end with copolymers. I think you can read on your own about copolymers. And olefin metathesis, that's above and beyond. If you go on to like an upper level, 300 or 400 level chemistry class that's about polymers, you'll talk about all this. But what I want to end with instead is step growth or condensation polymers. And these usually involve two monomers. And like I said, most of the time, maybe not always, but most of the time, the resulting polymer does not contain all of the atoms of the original monomer molecules. I think I pointed this out in a previous lecture just to let you know that it was coming. But the idea behind all of them is the same. We're going to cover what? Polyamides, which are also called nylons. We'll do polyesters. Actually, I guess this really should say something like the idea behind polyamides and polyesters is covered in chapter 21, respectively, because we learned about amides, we learned about esters and how they're made. And the idea is, if you know your chapter 21 chemistry, you know all you need to know in order to understand how to make polyamides or polyesters. And we'll also cover polycarbonates, like polyethylene terephthalate, and finally we'll cover polyurethanes, which are polymers of functional group that used to be called urethanes. Now we call them carbamates. So here's the idea, and the trick is going to be the same for all of them. In chapter 21, as I said, we learned that if you take an acid chloride and some amine, the amine can be either primary or secondary. There does need to be at least one hydrogen here. I left these other two bonds unspecified. They can be to either hydrogens or carbons. In any case, as a product, you will get the result, get the corresponding amide, and also, in this case, a molecule of HCl. That will be, you'll have the elements of HCl as an inorganic side product, but the major organic product will be an amide. So the trick that will play on the whole system is, what if we took a molecule that is 2 carboxylic acid functional groups on it? And then what if we took a diamine, a molecule that is 2 amino groups on it? Well, this acid chloride will react with this amine and make an amide, just exactly like this. The mechanism's the same as in chapter 21, but there's an amine on the other side. What's that going to do? It's going to find an acid chloride functional group, which will be attached to a benzene ring, on which the other side of that, there will be another acid chloride functional group, which finds an amine, makes an amide. Then you have 4 CH2s. Here's another amine that finds another acid chloride functional group, then benzene ring, then power to that is another one of these acid chlorides, which finds an amino group, and so on and so on and so on. So using the rules that we gave before as to how we draw the structure of the polymer, remember the main rule is inside the parentheses with the n. We always need the n there to show that there's an arbitrarily large number of copies of what's inside. Remember that everything that you put inside the parentheses needs to be the same as all of the atoms in the monomers that make it into the final polymer structure exactly once. You have to show every atom exactly once, not 0 times, not twice. And so what I've drawn here is only one correct way to draw this structure. There's a wide variety of other possibilities. Really what you're doing is you're closing in on the polymer chain, and you're simply showing inside the parentheses the repeating unit. But so to speak, you can slide those parentheses in either direction and it's fine. I chose to start at this carbonyl carbon. So I drew it and then the benzene ring, and then you get to the other carbonyl carbon. Then you get to the first amino nitrogen, there it is, NH, and then you have 4 CH2s, and then the next NH, which would then attach to another carbonyl, but we've already shown that carbonyl once. So we're done. We've accounted for every single atom that's in the polymer chain. But I didn't have to start there. I could have started here. I could have had parentheses, then NH, then 4 CH2s, then NH, then the carbonyl, then the benzene ring, then another carbonyl, and then another NH would come, but we've shown the NHs already. So we would be done. That would be equally good. There's a large number of other correct ways to show the structure of this polymer. So this is how nylons are made. And there's all sorts of things. I think dental floss might be a nylon. Surely a lot of sutures used in the medical industry are nylons, and nylons are nylons. And there's a large number of polyamides also that are used in consumer products. So what if instead of making amides, we made esters? Let's focus on that next. All right, waved my magic wand, and except I think I meant an oxygen instead of a phosphorus over here, I'm almost positive. Okay, so what if we did the same trick, but instead of using amines, we used alcohols? We already know that acid chlorides plus alcohols give esters. And incidentally, this doesn't even need to be an acid chloride functional group. We also know that you can do a Fischer esterification reaction. And so those conditions can be applied as well. Similarly, for the previous one, we used an amine and an acid chloride. You could also just as easily have used an amine and a carboxylic acid and our old friend ECC. Remember him from the proteins chapter. So I'm in all cases just giving examples of how these reactions can be done, but it's not the only way. You'll get an idea of the range of possibilities, I believe, when you in your OWL assignment, I think. At least that's what I would guess. So, but we certainly do know that if you alcoholize an acid chloride, you will get the corresponding ester, and essentially the equivalent of a molecule of HCl. Well, what if instead we used a diol and a diacid chloride? Well, this OH group on the diol will find an acid chloride functional group and make an ester, exact same mechanism as we talked about in chapter 21. Then you have two CH2s, then another carbonyl with another acid chloride. So an OH and another diol molecule will attack here and make another ester. That OH is attached to a CH2, then a benzene ring, then a CH2, then an OH. And guess what? That one finds another acid chloride, makes an ester. CH2 acid chloride finds an OH, makes an ester. CH2 benzene ring, CH2 OH, and so on and so on and so on. So again, in the structure of the polymer, we just want to be sure that we include all of the atoms that make it into the final polymer chain exactly once. We account for each one exactly once. So this will not include any of the small molecules that also get made, HCl, or if we used carboxylic acids in both cases, you'd get water molecules. So those atoms don't make it into the polymer chain. Again, that's why we call it that's why we call this a condensation polymer. These are condensation reactions. Good. So this is, I believe, one correct way of drawing the structure of the polymer. I chose to start at the oxygen of one of the OHs, CH2 benzene ring, CH2O, and that used to be OH, but now that oxygen is part of an ester functional group. And attached to this carbonyl, you'll still have the two CH2s just like before, then another carbonyl. The next atom would be an oxygen, but we've accounted for that one already. And again, I could just as easily maybe have started at this carbonyl carbon. C double bond O with parentheses here, CH2, CH2, C double bond O, O, CH2, benzene ring, para substitution, CH2, O, and then I think we're done. So there's always many correct ways to draw compounds like this. So that's how polyesters are made. There's a large number of those also that are quite commonly used. The next type of polymer I want to go over is polycarbonates. We first, in order to understand polycarbonates, need to understand what a carbonate is. And carbonates are a special kind of ester. You don't run into them very often, so I want to make sure that we understand those first. So that's where we'll go next. All right, and back we are, although mere moments passed for you guys. So in order to make a polycarbonate ester, like I said, one needs to understand what a carbonate is. And carbonates are a special kind of ester. They're essentially esters of carbonic acids, so a carbonate. So they have structures like this. So you can buy carbonate esters. They're not the most stable things in the world, but as long as you keep them cold and treat them with respect, they're fine. But conceptually, at least, you can make a carbonate by treating with alcohol. This diacid chloride, this molecule is known as phosgene, which I put the spelling of phosgene in your class notes. Phosgene is an exceedingly dangerous molecule. Phosgene was used as a poison gas way back in World War I, so it's not something to be trifled with. And there are other things that work essentially like phosgene. But conceptually, the idea is exactly the same as forming an ester from an acid chloride. It's just that it happens on both sides of the carbonyl, and you generate molecules of HCl plus your carbonate. So we're going to play the exact same trick. Phosgene is already kind of a difunctional compound. It's an acid chloride on both sides. But if we treated it with a diol instead of just a regular alcohol, well, this OH would look for a phosgene molecule, alcoholize it, and make an ester on this side. On the other, with the acid chloride on the other side, another alcohol molecule will find that and finish the carbonate ester. Then you'll have your 3CH2s, then OH, which finds another phosgene molecule. Another diol molecule finds the other side of the phosgene molecule, then 3CH2s, and then the next OH finds the phosgene, and so on and so on. So the structure of your polymer would look something like this. And once again, this is not at all the only correct way to draw the structure of the resulting polymer, but it is one correct way. I also, in case you were wondering why I seem always careful to make these bonds protrude through the parentheses, that is how it's generally done by convention. I think they're doing that to try to show that the chain is continuing an arbitrarily large number of times, n times, if you will. So that's all very much on purpose. And polycarbonates are your eyeglass lenses are going to be a polycarbonate almost certainly. Bulletproof glass is a polycarbonate almost certainly. And so it's just another class of step growth polymers. Last but not least, we need to learn one last new functional group, just like we learned about carbonates just now. And that functional group used to be called a urethane, but that's the old name. Nowadays, we call it a carbamate. So let's talk about polyurethanes next. Well, that took some doing, but I think I'm finally ready to show you about polyurethanes, or firstly, of course, about urethanes, which again nowadays we call carbamates. These are most generally made by a condensation reaction between an alcohol and a molecule with this functional group, which is called an isocyanate. And it's just another functional group that we don't run into nearly as often. These two species come together with a very chapter 21 type reaction. And I've given you the mechanism for a generalized isocyanate reacting with a generalized alcohol. Of course, R1 and R2 could be replaced with anything. These are generally considered to be done in acidic conditions, and you could expect that there would be an acid catalyst. And so the product is this carbamate or urethane. And the reaction is best shown by protonating the nitrogen first rather than the oxygen. Certainly you could protonate the oxygen also, and that makes another plausible pathway, but the simplest and most direct pathway comes by protonating that nitrogen. And then using the alcohol to attack that central sp hybridized carbon, which is under even more strain due to the adjacent plus charge in the nitrogen. That gets rid of the plus charge in the nitrogen, and then we just need another alcohol molecule to pull off the proton in this positively charged oxygen, and you get your carbamate or urethane. So I just leave that in there for your perusal. But anyway, that's how carbamates are made. I think we actually had a carbamate when we were talking about proteins. Weren't we protecting the nitrogen terminal of an amino acid with a carbamate functional group, a Bach or a Z functional group? So it's the exact same type of idea there. In any case, well, I guess we made those by a different method. So actually, we learned there's more than one way of making a carbamate, right? You could also take an amine and treat it with a chloroformate ester. That's what we did there. Anyway, all that aside, this time we're using it this way. I picked here a diol and a diisocyanate, and so they would do the exact same things we've seen. This OH group would find an isocyanate carbon to add into, then you'd get these two carbons, each with two methyls, and then it'll get this compound, that carbonyl group, for that central sp hybridized carbon will then find the OH group on another diol, which then goes through the four-membered ring. Why is there a four-membered ring? Because I feel like it. Yep, you knew that was the answer. Rest of the molecule then goes to the OH, finds another isocyanate carbon, makes a carbamate, goes to the rest of the molecule, and then the next isocyanate carbon finds another OH, and on and on and on. And this here, unless I've completely screwed it up, which I don't believe I have, that's just one of any number of correct ways to draw the structure of the polyurethane ester. So if the question were, draw the structure of the product of this diol with this diisocyanate, that or any of the variations on it would receive full credit, as long as You include within the parentheses every atom that makes it into the polymer chain exactly once. So something worth studying. And with that, I think we're done. So like I said, I will try to do my chapter 29 lectures for those who are interested. You will never be responsible for chapter 29, at least not in the spring 2020 term. If somehow this video lasts longer on my channel than that, and someone from a later class than that is watching this, you don't get off the hook. This was, of course, during the COVID pandemic, but you will not be responsible in spring 2020 for the chapter 29 material on either exam 4 or the final exam. This material on polymers, again, is fair game for the final exam, but will not be on exam number 4. So other than that, that's about it. It's been a right pleasure. I wish we could have done more of this in person, but oh well, it is what it is. In any case, have a good day.